worksheet from last week with you. This is the last problem that we didn't have enough time to get through. If you weren't here, that's fine. You can just take a picture of it. I'll put the problem up here so we have it. So this is still a dimensional analysis problem, much of what we were working on last week. This one's a little bit more challenging, but it's still something that I want you guys to be able to do. So I'll be honest, when I took this question, I took this from a previous exam. So it's reasonable that you could actually be asked something like this. So that's why I want to make sure that we go through. Now this question asks us to find the thickness of the wet paint, but this question is scaffolded in a way that you're going to kind of answer the parts that you need before it, so that's helpful. That's also how it was worded in the actual question as well. So you could reasonably expect to see this level of scaffolding in the question as well. Now there's a couple of equations that I want to give you, and there's one slight typo here that I want to talk about. So the first two equations that aren't on this sheet are the area and volume equations. So these you would probably be expected to know. These just come from your high school geometry class. Remember, area is length times width. And then volume is length times width times height. We can just talk about quickly how we actually get to that thickness equation that we're going to use. So if I look at these two equations here, what do I notice that they both have in common? The what? Yep, exactly. So if we look at both of these equations here, we notice that they both have length times width. And I know from the first equation that length times width is equal to area, so I can then combine these equations to get an equation that has both volume and area in it. So that's actually how we get to the one that we're going to use here. So I'm going to rewrite the volume equation, but now instead of writing length times width, I'm going to write area, so I can get those both in the same equation here. And then the h is left over. Now this one, we're just changing the name of the variable. It doesn't change anything mathematically. I actually left it like this in the problem, but more correctly, you should write that as a t instead of an h. And again, we're just changing the letter of the variable to reflect the actual problem. It doesn't change anything mathematically. It's just that we think of, the thickness of paint. We don't think about it in terms of height. So all we're doing is changing the letter there. So these are the three equations that we're going to have to use throughout. Again, the first two you do need to know. This one you might be given, either way. So if we look at step one, they're asking us to find the volume of the paint, and they're telling specifically which units we want to be in. So that should make it pretty straightforward. So the volume of the paint that they give us is in liters. So what I'm going to do here is I'm going to use an SI prefix to get to milliliters. Again, we spent some time on that last week. And then I'm going to use the conversion that 1 milliliter equals 1 cubic centimeter. So this one's not too bad. So again, we'll set this up. We have 3.79 liters. I know that there's 1,000 milliliters in 1 liter. I know the 1 liter has to go on the bottom because I need this to cancel out. So that's step one done. And then the second step, I'm just going to cubic centimeters. Again, remember that one is just 1 to 1, but that is another one that you need to memorize. So once I calculate all of this out, we're going to get to 3790 centimeters cubed. Now the units are important. I'll show you why they're important at the end, but for right now, we're just going to go to the units that they tell us to go to. So that's step one done. Step two, we need to find the area. So again, our goal is to use this equation here. We found the volume in step one. Step two, we're finding the area. But the order you do this in doesn't really matter. So if we remember what the equation is for area, it's length times width. Now we have to be careful here because if we're talking about area, so if I just use this equation the way it's written, I'd be talking about one surface. So I could be talking about the ceiling or one of the walls because area is 2 dimensions. But if we read the context of the problem, we're actually painting 5 surfaces here, right? Because we're painting all 4 of the walls and we're painting the ceiling. We're not painting the floor. So the actual equation that we're going to end up using is basically 5 times whatever we get. Because again, that's 5 surfaces. They tell us they're all equivalent, so they're all, the length and width of all of them are 6 by 6. So I can plug that in. So 6 meters by 6 meters. centimeters. And when I calculate this out, I'm going to get 180. What are my units after I calculate this?
Meters squared.
Yep, they're going to be meters squared because I multiplied these two units here. I didn't do anything else. So our units there are meters squared, and that makes sense. We have to do one last step though. So here the question asks us to get this in centimeters squared, and right now we're in meters squared. So again, we saw this at the end of last week. Remember how we do this. So again, that's just an SI prefix change. The only thing that we have to do is be aware of the squared units. So usually how I like to do it is just write what the regular prefix change would be. So remember there's 100 centimeters in 1 meter, and then you have to remember to square this. Because again, we have squared units here. If you don't do this, these units aren't going to end up canceling. Now remember, when you do this, you have to distribute that square to the number and to the unit. And you have to do that for both of them. So what that would actually look like if you wanted to write it out would be something like this after you've actually distributed it. And that's how the meter squared cancels here. The important thing for the math is that you make sure to square this number here, because otherwise you're not going to get the right answer. But once we do that, we get 1.8 times 10 to the 6th centimeters squared. Any questions on step 1 or step 2 with that? Okay. So now let's do our last step. So I'm just going to write these numbers up here because we're going to use them. We have our volume and we have our area, and they're both in the units that we want them to be in. Now we just need to figure out the thickness. We're at the last part of the problem here. So again, remember the equation for that is V equals A times T. Now, anytime we do math in this semester, I'm always going to show doing it this way. What I recommend you do is solve the equation algebraically first for the variable that you're trying to get to. I don't like plugging in numbers and then doing the math because it makes it hard to see where the actual units end up. So here we want to find thickness. So I want to get thickness on one side of the equation and then everything else on another one. Do that pretty easily just by dividing both sides by A. So then what I have is thickness equals volume over area. And we have both of these values here, so we can plug them in. So here we have 3790. And then this one we have 1.8 times 10 to the 6th. Now this is the actual part of the problem where those units that we talked about before become meaningful. So when we were answering the question as is, it might not have been clear why we needed to do this, but at the very end of the problem, this is where it becomes important. So here, what we want is we want to make sure that these have both the same units. So here we have centimeters, and here we have centimeters. The exponents don't need to be the same, and they often won't be. But what this allows us to do is, if we remember, when we divide exponents, we subtract them. So the units that we would end up here with are basically centimeters 3 minus 2, which is just 1, because again, you subtract the exponents when you do this. So then the answer that we're going to get here is 0.00211. And our units are just centimeters, because again, we have cubic centimeters here and squared centimeters here, so we subtract the exponents. We're not quite done, we're almost at the end. The question's asking us for the thickness in micrometers. Right now we have it in centimeters. So we just have to do one more step here. Again, you can do it in 1 or 2 steps. I'd recommend doing it in 2. So I'm going to go from centimeters to the base unit first, which is meters, and then I'm going to do a second step to get to micrometers. The only units left after this step are micrometers, and I get 21 point. So I know that question was a bit challenging and there's a lot of steps that we have to do. It's all stuff that we already know. It's just a matter of kind of applying it in this applied setting. Is there any questions on how I got to this or any of the steps that we did along the way? So just make sure you know how to do this problem. Maybe practice it again before the exam. Could end up being helpful. So that's all we're going to really do for dimensional analysis stuff. We'll move on to chapter 2 stuff. The first thing that we're going to deal with are the protons, electrons, and neutrons. Now, if you took Chem 100, this is going to be a bit of a review for you, but it's still important because we need to use it in this class. So there's 3 subatomic particles. There's protons. What's the charge on a proton? Yep, it's positive. So oftentimes, at least my shorthand, I'm going to write this as P+. And you might want to do that as well because that can help remind you what the charge is. The other one that we have are neutrons. These are neutrally charged. I'll often just write this as an N, and then electrons. Electrons I like to write as E- because again it tells me what it is and it also reminds me of what the charge is. Now let's quickly just do a refresher on what the structure of an atom looks like. Now this isn't going to be very scientific, but it'll give you the pieces that you need to know. So we have the nucleus. Which 2 of these particles make up the nucleus? Yep, it's going to be protons and neutrons. So if we kind of draw a couple in here, what we have. Again, not drawn to scale, but those are the 2 particles that are in here. Now, one question that you could be asked is there's questions that ask you what is the nuclear charge. So to figure that out, we have to just remind ourselves what's in the nucleus and then think about what the charge would be. So in this situation, if I asked you what is the nuclear charge of this atom, it would be +2, right? Because I have 2 protons in here, the neutrons don't have a charge. So that question actually is really just asking you how many protons you have, because that's what the charge is that you have in the nucleus. You just have to remember to put the plus in front of it. The other thing that we have are going to be electrons. And I'm just going to draw these around it. These are not in the nucleus, so these are surrounding this, and we'll talk about orbitals later in the semester and talk a little bit about how those are arranged. Okay, so the next thing that I want to talk about is writing nuclear symbols, so kind of applying this to an actual problem. So this is going to be the general formula of one of these nuclear symbols. The X tells you what the element is. That just comes from the periodic table. So that's why either in this class or a previous chem class you were asked to memorize that. That's where you're going to need to use it. This A, actually I wrote this upside down, sorry. A should be on the top. The A here is going to be the mass number. And this is going to be the number of protons plus the number of neutrons that we have. So we add those together. And then Z is the atomic number. 2 important pieces of information here. One, the atomic number is the number that you see on the periodic table. So we see these blue numbers above each of the elements. These are the atomic numbers. What that also tells us is that tells us the number of protons. Now we're going to talk in just a little bit about isotopes and ions and stuff like that, where some of the other particles can change, but you're never going to change the number of protons. That is always going to stay the same, and that's always going to be what tells you what element you have, basically. So if we look at an example problem, let's say I have something like carbon 12. And they want me to write the nuclear symbol for that. So we can talk about briefly how I would do that. Now this number that comes after the dash, if they're giving this to you in a word problem, that's telling you what the mass number is. So that's important. So first thing that I'm going to do is write the element symbol. So I'm going to write the symbol for carbon, which is C. I'm going to put the mass number in. They gave us that in the question. It's 12. The other thing that I need is the atomic number. And I can find that pretty easily because I know what the element is. So if I look at the periodic table, there's a 6 above that. So that tells me what the atomic number is. Now let's talk about some other types of questions that you can see here. So let's say they want to know the number of protons, neutrons, and electrons. Okay, protons would be very easy to figure out here because again, that's equal to the atomic number. So the number of protons that we would have is 6. The number of neutrons, that's going to come from our knowledge that we already know, which is the number of protons and then the mass number. So I know that the mass number is equal to the number of protons plus the number of neutrons. So if I just want to get the number of neutrons, it's going to be the mass number minus the number of protons. So here the mass number is 12, number of protons is 6. I'm also going to end up with 6 neutrons. And I can confirm that because 6 plus 6 equals 12, which is the mass number that we see. Another question that we could be asked, what is the number of electrons that we have here? Now, this one we have to pay attention to some additional stuff. So if there's no charge, that's going to mean that the number of electrons is equal to the number of protons. And again, a charge they have to tell you. So they either need to give it to you in the problem, or they could tell you an ion. So for example, I could tell you lithium ion. There's a few ions that you do have to know what the charge is just by telling you that. So I'll tell you what those are. So there's a few columns in the periodic table you're going to have to memorize what the ion charges are. And they're pretty easy to remember. So this first column over here, these are always going to be +1 ions. This one we also need to know, these are always going to be +2 ions. The transition metals we skip over, you could be asked a question about these, but they have to tell you what the charge is, because these ones have a couple of different charges they can have, so there isn't just one charge that we can predict based on what column it's in. So we skip over that. This column we need to know as well, so these ones are going to be +3. Now this column that we have here that starts with carbon, these are technically ±4, but you probably won't be asked that, so don't worry too much about that column. But the next 3 we definitely do need to know. So this column here is going to be -3. So notice the trend. We had +1, +2, +3, -3. This one's going to be -2. This one's going to be -1. So really for those 6 columns, you have to memorize what those charges are going to end up. Now here we didn't have to worry about that because we just had a neutral carbon atom. So the number of electrons here is just going to be 6 as well. Now if we do have something that is a charge, so for example if we had lithium plus for example, then we are going to have a different number of protons and electrons. So the charge is equal to the number of protons minus the number of electrons. So here we didn't have a charge, so the charge would effectively be 0, and that makes sense if we plug in those values, because 6 minus 6 would be 0. So that's how you can figure out the charge if you do end up with an ion there. The last thing that you could be asked is what is the nuclear charge? Again, we talked about that over there. It's essentially just equal to the number of protons, but you have to include the plus here. So you can't just write 6 for nuclear charge because that's not accurate. The charge is +6. Because I have 6 protons in the nucleus, that's the only thing that's giving me charge, so it's going to be +6. Any questions on any of this stuff? Okay, so I'll hand out the worksheet for today. That will give us some practice looking at those. So what I'd like you guys to do is try to get as many as you can done with this table here, and then question 2 you should be able to answer as well. So one thing I forgot to mention, this shouldn't really come up, but this does come up in some questions. If they don't give you a mass number and there's no logical way to get to it based on the information that you have, what you want to do is pick the number that's closest on the periodic table. So for example, the strontium question, this first one, there's actually no way that you could get the mass based on the information that I gave you. So here you just round it up to 88. So 87.62, just round it up to the closest one on the periodic table. You shouldn't encounter too many problems like that, but just in case you do, that's how you do it. So it's okay if you're still working. The goal is really just to get you to work on some of the problems and then think about what we just talked about. So what I'm going to do is I'm going to put the answers to that table up on here so you can either write them, check them, take a picture of them, whatever you need to do. The only thing here is this beryllium 4, I tried to cross off with marker. It should be beryllium 9, but everything else on the table should be what it is. So I'll give you a minute to look this over, and you can also see if there's any questions that you want to ask, or if you want me to work through one kind of review here. So I'll leave that up till the end of class, but is there any questions on just number 1 that you guys want to ask? Okay. So then let's talk about 2. So 2 is a multiple choice question. This one says an atom has 17 protons, 18 neutrons, and 17 electrons. What is the correct representation of this atom? So the way that I would approach it, and really the way I would approach any of these questions, is the number of protons. I like to anchor myself to that part because I know that that part's not going to change. We can change the neutrons and sometimes the electrons if we have a charge. But here they're telling me that I have 17 protons. So right away what I'm going to look at is I'm going to look at the periodic table. I'm going to see which one has the atomic number of 17. So that's going to be this one here. So right off the bat, I know this has to be chlorine because I know that the number of protons doesn't change. That's helpful here in a multiple choice question because I can already rule out B and D just based on that one part there because I know that the element has to be chlorine. So then we just need to figure out the other part of it. So now it's between A and C. And we know that our element is going to be chlorine. Remember the mass number goes on top. The mass number is the number of protons plus the number of neutrons. So here they give us that. So 17 plus 18 is 35. Now that actually is enough to give us the right answer right there, which is A. The bottom part, if you wanted to complete it, again, that's the atomic number, that would be 17, and that's equal to the number of protons. Any questions on those first 2 problems? Okay. So now I'll move on a little bit to the next topic, which is isotopes, and that'll probably be the last thing that we're going to have time for today. So isotopes are just building off of everything that we just talked about. The formal definition for this is that these are going to be atoms of the same element. But with different mass numbers. So I think we saw an example of this in this table. So here we have chlorine 37 and chlorine 35. So that would be an example of a pair of isotopes. But let's actually think about what this means for a minute. So if we think about what mass number is, remember it's equal to the number of protons plus the number of neutrons. Now if I think about this definition here, the first part, they're the same element. So that means that the number of protons cannot change because it's the same element. So what that also means then is that if this one is always going to be the same, if we're with the same element, the thing that's going to be changing is the number of neutrons. So that's important here as well. Okay. The other thing that I want you to know is the average atomic mass. And this is going to be the average mass of all of the isotopes. And importantly, it's a weighted average. Okay. So the number that you see on the periodic table, so for example, if we look at chlorine, we've been using that as an example, this orange-red number here, this 35.45, that's the average atomic mass. So if we took the mass of all of the isotopes and we did a weighted average of it, it would be 35.45. And again, we see that in that question there, we had two different isotopes. Now the equation that we use to calculate this, we want to calculate the average atomic mass. It is just a weighted average, so if you know how to do that, this will make sense, but I think some people would still benefit from writing the whole thing out. So essentially, we're just going to have as many terms as isotopes that we have. So I'm just gonna do this from 2, but if you have more, it's very easy to change. So the first term is going to be the percent abundance, and they'll usually give you that in the question, of isotope 1, so I'm just gonna write that as I1. Importantly here though, you have to make sure that this is as a decimal. Okay, so if I gave you something like 80.1%, for example, you wouldn't put 80.1 here, what you would put is 0.801. So remember, if you're going from a percent to a decimal, you just move the decimal place over 2 places. So that's the number that you would want to put in here. Again, you shouldn't have anything bigger than 1, because that would indicate that you have 100% of it. Then you're going to multiply that by the specific mass of isotope 1, and again, they'll usually give you that specific mass in the question. So that's the first term, and then you're just going to repeat this for however many isotopes that you have. So I'm just going to do it for 2. So if I wanted to deal with the second isotope, it would be the same thing. So you'd have percent abundance of isotope 2. Again, you need that as a decimal, not as a percentage. And then you'd multiply that by whatever the specific mass of isotope 2 is. Like I said, if you had a third one, you would just add a third term on, the exact same one. You can do it for as many as you want, but this should at least give you an idea of how to set it up. Any questions on that? Okay. So what I'm going to have you do is I'm going to have you try 1, 2, and 3. Now what I'd like you to do here is start with number 2. So try to get as far as you can on number 2 for this one. If you have leftover time, think about one.
What is the average atomic mass of
know some of you are still working, but I want to start going through this one just to make sure that I have enough time for this one. So 2 is asking us to calculate the average atomic mass. So again, we're going to be using this equation here. What we're going to need to calculate that is we're going to need these 4 numbers here. So let's actually take note of what they give us in the question. So we have XX 101, XX 102. So what we need is we need the mass and we need the percent abundance. So let's look in the question and see what they give us. They give us the mass of both of them. So the 101 is 101.32. Again, we have to use the specific mass, not just the number that we see here. And then for 102, we have 102.001. Now for the percentages, they only gave us one of them. So they gave us the 101, that was 83.5. Again, remember when you use this in the equation, it has to be as a decimal. So the way that you would input this, 0.835. But right away we see a problem, so they don't give us the other percentage. So how are we going to get the other percentage since they didn't give that to us? Yeah.
I'm not sure if this is right, but could you just do 100 minus 83.5 to get the other percentage and convert that to a decimal?
Yep, that's exactly what you have to do here. So I know that there's only 2 isotopes, so what these percentages have to add together to be 100%. We already know what one of them is, so we're just going to subtract the 83.5 from 100, and that gives us 16.5%. And again, as a decimal, that would be 0.165. So now we have the 4 numbers that we need to use this equation here, so we just need to plug them in. So the first term we'll just do for the 101. So the mass is 101.32, and then we multiply that by 0.835. So that's dealing with the 101, and then the 102, we have 102.001 multiplied by 0.160. And then when we type this in our calculator, that will give us the average atomic mass. So what we get here is 101.43. Now the units that we're going to use for right now are AMUs. So when we're doing average atomic masses, that's what you want to use. It's fairly equivalent to grams per mole, which you're going to see in a little bit. But for right now, we're just going to use that as our units. So any questions on that one, how I did it? Okay. So let's just quickly talk about the other 2. So question 1 was more of a conceptual question. So this one says rubidium has 2 isotopes, rubidium 87 and rubidium 85. Which isotope is more abundant? So remember, the average atomic mass is the number that we see on the periodic table. And remember, that's a weighted average. So the average that we see is going to be closer to the isotope that we actually have. So if we look at rubidium, for example, we see that the average atomic mass is 85.47. So I know the only 2 isotopes that I have are 85 and 87. This average here is a lot closer to 85 than it is to 87. And again, that's because it's a weighted average, so what that means is that I would have more of the 85. Because again, it's weighted, it accounts for the amount that you have. And then number 3 is a multiple choice question. So this one says, which of the following statements is correct regarding isotopes of the same element? Assume that we have neutral atoms. So the correct answer here is actually the first one, A. They have the same number of protons and electrons, but they have a different number of neutrons. So that's exactly what we talked about right here. We talked about that. So let's talk about why the other ones are incorrect. So B, they have the same number of neutrons, but different number of protons. So that's basically the opposite of the point here. Remember, the number of protons never changes. So B is incorrect. C, they have the same mass number. That part's already incorrect, because again, they're going to have different mass numbers. And then the second part, they have different atomic numbers. That's also incorrect, because again, the atomic number for an element is never going to change either. So C is incorrect. And then D, they have different number of protons, neutrons, and electrons. Again, protons can't change, so that one's incorrect. So here the correct answer is A. Any questions on any of those 3? Okay. So I think I'm going to stop it there for today. So the only thing that we didn't get to on the worksheet is the naming. That's what we're going to start with next week. So I'm still going to cover it. If you want, you can bring the worksheet with you, and then we'll talk about that.